Let's take a look at the question here. List some terms associated with waves. This is just in general things that you remember from maybe physical science or grade school. Yes? Frequency is one. What are a few others?
Different heights.
Different
That's
heights.
like frequency.
And what do we call heights when we're talking about waves? Anybody know? It starts with A.
Alpha waves.
Ocean waves. I'm a little lost.
Ocean waves, sure.
I'll just say asymptotes.
Not asymptote. It's amplitude. That's the height of a wave. Anything else?
Isn't it wavelength?
Wavelength is another good one. Yep. Good. Yeah, those are all real good ones. I heard frequency, I heard amplitude, I heard wavelength. Any of those are just fine to answer this question. So the main thing we're going to do today is get a little introduction with waves. And that is what we're going to be talking about in this chapter, and how light behaves like a wave. In the previous chapter, we looked at how light behaves like a particle. We treated it as though it was just a small ball, or like a ping pong ball. I'd often say when it goes and hits a mirror, you can think about what would happen to a ping pong ball when it hits a mirror like that. It's going to bounce off in a certain direction. So we were essentially treating light waves like we were treating light as though it was a wave, as though it was a particle. And in this chapter, we're going to be treating it like it's a wave, and we're going to see some of the different wave-like properties on how light actually does things that waves do. So in order to do that, we got to figure out exactly what waves are and a few of their characteristics. So we need to just go to the back of the room briefly. I'm just going to pause the recording. Start up. Welcome back. We're going to be taking some notes on waves right now. So loosen up your hands, get something out to write with. You can title your notes today, Waves. The first thing I'd like you to write down is principle of superposition. Principle of superposition.
Superposition.
You got it. Principle of superposition. And after you write that down, write, when two waves meet, the result is a sum of their combined shapes. When two waves meet, the result is a sum of their combined shapes. In other words, if you've got waves that are going towards each other, and let's just say, to kind of make this clearer, let's say you've got a triangle and you've got a square, and these waves are heading towards each other. What the principle of superposition says is that when they're in the same location, when they're interacting in the same spot, the result would simply be adding their shapes together. You would have a triangle on top of the square. If we could actually make waves that looked exactly like this, and we sent them down towards each other like we just did in the back of the class, this would be the result. Of course, with the slinky, we can just make little, lumps going towards each other, so the best we could do was see a bigger lump when they met up. But if you actually had distinct shapes, that's the sort of thing you would see. So again, that was, it's just a sum of their combined shapes. So then the other thing we have to consider is what happens after this interaction. And what happens after these waves interact, we've got two choices, right? They're either going to bounce off each other and come back where they came from, or they're going to go through each other towards the other end. Any guesses on which one that ends up being? I'm many people think that the waves are just going to pass right through each other? How many people think they're going to bounce off each other? Okay. Sorry, you're actually all wrong. They do go right through each other. So these waves, when they're coming towards each other like this, they interact, and then they just pass through each other as though nothing had happened. And so the next picture in this would be the square further on the left, and the triangle on the right.
Right, so the house isn't the result?
Well, this would be the result in that spot for that one point in time when they're in the exact same location. But a little bit later, they would move off in their respective directions. The box would continue left, the triangle would continue to the right. So if you want to draw this, that's fine. If you're more of a words person, you could say the waves pass through each other, they don't bounce off each other, as long as you have that information in your notes. The other thing I'd like you to write down somewhere is has to do with the wave speed. This is something we'll be coming back to time and time and time again. Write down somewhere the only way to change the speed of a wave is to change the medium it's traveling through. The only way to change the speed of a wave is to change the medium it's traveling through. And so whether you have a transverse wave or a longitudinal wave, those two waves that we saw in the back, if you keep the medium the same, if you keep the tension in the slinky the same, they're both going to be traveling the exact same speed the entire time. The only way you can change the speed that wave is moving is by changing the actual material or the substance or whatever it is that the wave's passing through. And we did that in the back by increasing the tension. When I increased the tension, I was changing the medium that the wave was traveling through, and that caused it to go faster. Questions up to this point? All right, just a couple things about the two different kinds of waves here. You can draw something like this in your notes. We'll point out a few different characteristics. This is known as a transverse wave, so you can label that somewhere. A lot of different characteristics about this one. So, we mentioned a couple of them earlier. One was amplitude. Amplitude is simply the distance between the crest of a wave, the high point, and the middle point here. So you would call that amplitude. I'll just go through the ones we mentioned first. One of the other ones you guys said was wavelength. And wavelength is just the distance between the two crests that we see here. So we've got this crest and this one. The distance between those 2 points is going to be known as a wavelength. And wavelength has an abbreviation that looks like this. It's a little Greek letter. Greek letter lambda, if you're curious. And it represents wavelength, because wavelength is a long word. If we abbreviate amplitude, it would just be with capital A. So wavelength, amplitude, I think someone also mentioned frequency. We'll get to that shortly. A couple other things we need to point out about this. A little bit about the highest point of your wave. As mentioned, this is a crest. Anybody know what the lowest point is called? Starts with a T. R. O. U. Trough. Absolutely. So crest is the high point. Did you say troll?
Some trouble.
Oh, trouble. Well, you can call it trouble if you want. So a trough is the low point of our wave. Crest is the high point. Just a few other things that I need to mention with respect to this, and that has to do with these points right here. You can see there's that little dotted line going right down the middle. The spots on the wave that are in that middle location are called nodes. N-O-D-E-S. So that would be a node, that would be a node. Probably the least important thing about this is something called an antinode. So if this is a node, anybody have a guess as to what might be an antinode? The lines?
Yeah.
Which lines?
The ones that have no frequency or amplitude.
That have no frequency or...
Or like the no crest.
Oh, like crest.
Finish, right?
Finish?
What?
What's going on?
The line before
Like
and the line after.
the lines.
Oh, like this.
No,
No, like
the
the one
horizontal
on
line.
Before. The
Like
black
before
part,
it
the black
starts
part.
Oh, this part.
There.
Yes.
Oh, okay. No, good guess though. I have such a hard time hearing people through these masks. I can't wait for this to be over. Okay, yeah. So not that. What your antinode is if your node is this part in the middle of your wave, the antinode is just going to be the far away part of your wave. In other words, a crest or a trough. So antinodes are also known as crests and troughs. So however you want to word that. And those are some characteristics about waves. And as long as you are a little familiar with that, you should be just fine. Now the other kind of wave that we have is a longitudinal wave. And maybe that'll look something like this. The main thing is you've got this compression, and that compression is moving from one end of the wave to the other. So this is called a longitudinal wave.
Mine does not look like that.
That's okay. There are really just three things that you need to know about longitudinal waves. So this part here and this part here that are kind of compressed, we call those compressions. The parts that are stretched out like this, we would call those rarefactions. That's kind of a strange word. And the last thing that we need to talk about with longitudinal waves is how you would figure out its wavelength. Wavelength is probably the most important thing we'll be dealing with on a regular basis through all this stuff. So your wavelength, in the same way as over here, it's from crest to crest. Here, it's going to be compression to compression. Or you could do rarefaction to rarefaction, but it's kind of hard to see the middle of where that is because it's so stretched out a lot of the time. So wavelength is just going to be from compression to compression in the middle of the compression to the middle of the other one. All right, a few more things we need to talk about. Today's mostly about learning the terms and some of the basic things about waves, so we can start applying some of these things to light. The other things you need to know, and you mentioned them already, is frequency. So you're going to want to write frequency down. And I abbreviate frequency with a cursive F. If you just want to use lowercase, that's fine, as long as you're remaining consistent. Frequency is just something where you measure how frequently wave crests pass a certain point. So you can write that down. And frequency is measured in a unit called hertz, Hz. And what that means is it's how many seconds per, how many waves per second, I should say, are passing a certain point. So if you've got, 4 wavelengths passing one spot in 1 second, your frequency would be 4 hertz. That's what that means. It's a measure of how quickly these waves are going by a certain point. The other thing that you need to know is period. And period is abbreviated with a capital letter T. The units on that are seconds. And when I write seconds, I have it as a cursive S, just so it doesn't look like a 5 or something. But you can use regular S if that's something you want to do. So a period basically measures how many seconds per wave. In other words, you've got a certain wavelength from crest to crest, and it takes that wavelength a certain amount of time to go by one position. So maybe you've got these 2 crests, they're moving along, and however long it takes for those 2 crests to pass this one point right here in this spot, that's what your period is going to be. It's simply how long it takes for the crest of one wave and the crest of the next wave to pass a certain location. So that would be the period of time it takes for one wavelength to pass. So that's frequency and that's period. The quick and easy way to try and remember what these represent is best thought of in terms of these two things. If you're just looking for a quick way to remember, am I dealing with period, am I dealing with frequency, just think about it in terms of the units that they're measured in. Period is measured in seconds. It's how many seconds there are between two wavelengths. Frequency is measured in how many waves are occurring each second. So if you're measuring how often these crests are passing one location, that is going to be something that's measured in hertz. It's going to be your frequency. So it's important to know the distinction between these two. Any questions on the difference between them? The good part, too, about these two things is that they're related. Period is equal to 1 over frequency, and frequency is equal to 1 over period. So you need to know that relationship, too. Now in math, we have a term, a way to describe this kind of a relationship. You know, if you've got two different things you're looking at, period and frequency, and when one goes up, the other goes down, anybody know what we call that relationship? It starts with an I. Yeah, they are inversely proportional. So it's a term that you should be familiar with. As one goes up, the other goes down. A lot of words, isn't it? We're just used to drawing lines. This is one of the more wordy note-taking sessions, so this isn't very typical. Now, of course, there's another type of relationship out there. If it's not inversely proportional, it could be the other one. Anybody know what that one is? So it starts with a D. Yeah, directly proportional is the other one. And that is a way to describe an equation that you need to know. You guys are familiar with the triangle relationships between variables, right?
What?
So if I would have a V here, and a wavelength, and a frequency, that would mean that V, velocity or wave speed, is equal to wavelength times frequency. Wavelength would be equal to velocity divided by frequency. Frequency would be equal to wave speed divided by wavelength. So that's the relationship between those things inside that triangle there. Now, if I would take this velocity and I would take this wavelength, and if I would say that the frequency is going to stay the same, if the frequency remains the same and I change one of these two things, the other one has to change in the same way. So if, let me write it out. So if my frequency remains the same and my wave speed goes up, my wavelength has to go up too to compensate for that. So that's why this is directly proportional. As one goes up, the other has to go up too. So that's something that you need to know. Directly proportional is the opposite of inversely proportional. This seems like a lot. but it's just a lot of words and some terms that we. Do I have an extra pro in there?
Yeah, proportional.
I'm going to leave it like that. Proportional. So I'm just going to take you through a quick example, show you a couple more things, and then you should have a good amount of time to get started on the worksheet, which will be due on Wednesday. But a lot of this is just working through some problems to get familiar with this vocabulary so that you can actually have some idea on how to deal with these waves. Because if we're going to talk about how light behaves like a wave, we've got to have at least a basic understanding of how these waves are working. All right. It's about time we have a picture here. There we go. This equation is on your formula sheet too, in the waves section. So if you'd rather just go there for it, that's fine too. So that's our setup here.
That's a lot of variables.
Sure is. Good thing we got 3 of them already. Now the 2 equations that we're going to be using to figure all this stuff out, one of them is going to be the one that we just had up there. Bless you. Where we've got wave speed on top. We've got wavelength and frequency on the bottom. And the other one, which is also on your formula sheet, is a pretty common distance equation. Distance is equal to velocity times time, or velocity is equal to distance divided by time. In physics, we use the letter x for position, for distance. So that's what the letter x means. It's how far you've gone horizontally. V is velocity. And again, this little thing, this is a cursive F, that's frequency. You don't need to use cursive like I do. I kind of grew up with it, and sometimes, like as in the letter S, when I use that for cursive, That helps me not think that it's the number 5. So, oh, go ahead.
Is the lowercase t the time?
Yes. All right, so we want to work through this and try and figure what these numbers are. So what is the wavelength in this problem? Yep. All right. So 1 out of 6 is done. What is the distance traveled here? X, horizontal distance. 10 meters. There we go. Third of the way through. What is time? 2 seconds. We're already halfway done. We haven't even done any math yet. That's the best kind of work, isn't it? Now we got to solve for velocity. So let's see. If I want to solve for velocity, I could go to this equation, right? Velocity is equal to wavelength times frequency. So I've got my wavelength, and I'm not given a frequency. Yes? Exactly. Yep. There's 2 velocities here. And if this equation doesn't get you the answer that you want, just try the other equation. And so we're going to take a look at this equation right here. Velocity is equal to distance over time. We have distance and we have time. So distance is 10. Time is 2. That means the velocity is going to be 10 divided by 2, which is 5. Units then are meters per second. So now I'm going to solve for frequency. Frequency is down here. I have my speed. I have my wavelength. So I can just use those numbers to calculate the frequency. It's wave speed divided by wavelength. So when you go ahead and calculate this number, you're going to end up with 1.25. And again, the units on frequency are hertz. That was on the back of one of our physics t-shirts probably 3-4 years ago. Something like it hurts so good or something. Spelled H-E-R-T-Z. Good times. And it's time for period. Oh no, we don't have an equation for period. And this t is just time. It's not the actual period. So how do we calculate period? Who can help me out? That's exactly right. Is that what you were going to say, Zach? Yeah. So period is going to be equal to 1 divided by frequency. If you have one, you can always calculate the other. And so the result of that is just going to be equal to 0.8 seconds. Very good. So I just kind of wanted to get you familiar with using these 2 equations in order to solve for a lot of these things. A lot of this is just going to be you going through and giving it a try on your own. What I'm going to do is I'm going to pass out the homework, and then I'm going to show you 1 or 2 more things, and then we'll call it a day. This worksheet will be due on Wednesday. The most difficult problem on this worksheet is problem number... Problem number 6 always gives folks issues. Do the best you can with that one. You do have all the information you need to figure it out, but be patient with yourself on that one. It might take 1 or 2 attempts to try and get the right answer there. A lot of times, too, on the front page, I'm asked, what do you want the measurements in when you're determining wavelength and amplitude? Because you got to use, something that measures. I prefer having things in metric for this because we always deal with metric in physics. If you've only got a ruler that has inches, that's okay. The main thing is that you're measuring the right thing. So, there's that. One last question before I show you a couple flashy things. In this example, when the wave is traveling to the right, how would we change the speed? Like, what would happen if I made this amplitude way bigger? Would that change the speed at all? No. What do I got to do to change the speed in this wave? Different medium, right? The wave, something about this string would have to change. You'd have to like stretch it more or compress it more. You'd have to change what this wave is traveling through. Even if you change this from a transverse wave to a longitudinal one, like a compression wave, that would not change how fast it's moving. You'd have to just change the medium that it's traveling through. Okay. So you can see different parts of this wave, and they're kind of like little bubbles there. What do we call this spot right here? That's a node. What do we call these spots right here? Yep, crest and trough, absolutely. Let me know when I've gone a full wavelength, okay? Right here? Okay, so this is kind of tricky because you see these as bubbles, but in reality, the string, if it's up here, would go down to the bottom here and then come back up right there. So this is something we'll talk more about later. But a full wavelength would go from here to here. Because here you'd have a crest, down to a trough, back up to a crest. So I just wanted to point that out a little bit. You can do all sorts of fun things with this. Anyway. More fun than a teacher should be allowed to have.